Welcome to this tutorial on industrial instrumentation. In this tutorial, we will talk about temperature measurement part 1, and the topic we'll cover is basics of temperature measurement. In this discourse, we will talk about temperature scales, that is Fahrenheit, centigrade, Kelvin, Rankine, and Reaumur, and their interrelationship. The term temperature is defined as the condition of a body by virtue of which heat is transferred to and from other bodies. The degree of a body or an environment is measured on a definite scale. The temperature cannot be measured directly, but is measured by observing the effect that temperature variation causes on the measuring device. The principal methods of temperature measurement are non-electrical methods, that is field-in thermometers, electrical methods comprising RTD, thermistor, thermocouple, and then we have radiation methods like pyrometers. There are primarily 5 scales of measurement that are related to temperature, and they are Kelvin scale, or the absolute temperature scale denoted by capital K. It is also the SI unit of temperature, which is one of the 7 fundamental units. 0 Kelvin or K denotes the absolute zero, which is theoretically the lowest achievable temperature. At 0 Kelvin, the molecular motion ceases to exist. The second is the Celsius scale or centigrade scale. It is symbolically represented as degree C. Third, we have Fahrenheit scale. It is symbolically denoted as degree Fahrenheit. The fourth is the Rankine scale. It is denoted as degree capital R. Along with the Kelvin scale, it also forms the absolute scale, that is 0 Kelvin is equal to 0 degree R. Lastly, we have the Reaumur scale. It is denoted as degree RE or degree small r. Here we will take a bit of time and see the interrelationship between the 5 standard temperature scales. From Kelvin to Celsius, we have degree C equal to K minus 273.15. Kelvin to Fahrenheit, we have degree F equal to K minus 273.15 within bracket into 9 by 5 plus 32. From Kelvin to Rankine, we have degree R equal to K into 9 by 5. From Kelvin to Reaumur, we have degree RE equal to K minus 273.15 whole into 4 by 5. From Celsius to Kelvin, we have K equal to degree C plus 273.15. From Celsius to Fahrenheit, degree F equal to degree C into 9 by 5 plus 32. From Celsius to Rankine, we have degree R equal to degree C into 9 by 5 plus 491.67. From Celsius to Reaumur, we have degree RE equal to degree C into 4 by 5. Moving to the third scale, Fahrenheit to Kelvin, K equal to degree F minus 32 into 5 by 9 plus 273.15. Fahrenheit to Celsius, we have degree C equal to degree F minus 32 whole into 5 by 9. From Fahrenheit to Rankine, we have degree R equal to degree F plus 459.67. Fahrenheit to Reaumur, we have degree RE equal to degree Fahrenheit minus 32 whole into 4 by 9. From Rankine to Kelvin, K equal to degree R into 5 by 9. Rankine to Celsius, degree C equal to degree R minus 491.67 whole into 5 by 9. Rankine to Fahrenheit, we have degree F equal to degree R minus 459.67. From Rankine to Reaumur, we have degree RE equal to degree R minus 491.67 whole into 4 by 9. And finally, from Reaumur to Kelvin, we have K equal to degree RE into 5 by 4 plus 273.15. From Reaumur to Celsius, we have degree C equal to degree RE into 4 by 5. From Reaumur to Fahrenheit, we have degree F equal to degree RE into 9 by 4 plus 32. And finally, from Reaumur to Rankine, we have degree R equal to degree RE into 4 by 9 plus 491.67. So these are the interrelationships between the 5 standard temperature scales. There are few temperature points which are very important from temperature measurement perspective. Those temperature points are listed below. Absolute zero, it is the lowest possible temperature theoretically. It is the temperature at which molecular motion completely ceases. In SI unit, it is at 0 Kelvin or 273.15 degrees Celsius or minus 459.67 degree Fahrenheit. The next is lower fixed point or ice point. It is the temperature of ice prepared from distilled water at 760 mm of mercury. Liquid and solid water are at equilibrium. The temperature is 273.15 Kelvin or 0 degree Celsius or 32 degree Fahrenheit. The third is upper fixed point or steam point. It is the temperature of steam prepared from distilled water boiling at 760 mm of mercury. Water vapor and liquid water are at equilibrium and the temperature is 373.15 Kelvin or 100 degrees Celsius or 212 degree Fahrenheit. Next we have boiling point. It is the temperature at which substance changes from liquid to gas. The freezing point is the temperature at which substance changes from liquid to solid. The triple point is a particular temperature and pressure combination at which all three phases of one substance can coexist in equilibrium. The triple point for water is observed at 273.16 Kelvin or 0.01 degrees Celsius or 32.018 degree Fahrenheit. When the partial vapor pressure is 611.657 Pascal or 6.11657 millibar or 0.00603659 atmospheric pressure. According to Gibbs phase rule, a three-phase situation is a component that leaves it with no degree of freedom. There are few laws which are pertinent to understand in the context of temperature and its measurement. Given below are the names of these laws. These laws are Seebeck Effect, Peltier Effect, Thomson Effect, Thermoelectric Effect, and then we have law of homogeneous material, law of intermediate material, and law of intermediate temperature. We'll speak about each of these laws in detail in the subsequent slides. The first of the thermoelectric effect is the Seebeck effect. The Seebeck effect is a physical phenomenon where the temperature difference between two dissimilar elements or electrical conductors generates a voltage between the two elements. With heat being applied to one of the two conductors, the heated electrons acquire energy and tend to flow towards the cooler surface. As these electrons move from the hotter end to the cooler end, a current starts flowing in the opposite direction as shown in the figure below. The voltage developed and the magnitude of the current depend on the temperature gradient between the two dissimilar elements. The Seebeck effect is numerically represented as J equal to sigma into minus del V plus E, where E is the EMF developed, J is the local current density, V is the local voltage, and sigma is the local conductivity. And the EMF of voltage generated is given as E equal to minus S del T, where S is the Seebeck coefficient and del T is the temperature gradient. The second effect is the Peltier effect. The Peltier effect is the reverse phenomenon of the Seebeck effect, where the electrical current flows through junctions connecting two dissimilar elements that emit or absorb heat per unit timescale at the junctions in order to balance the chemical potential difference between the two elements. In simpler terms, when electric current flows through a circuit comprising two dissimilar elements, thermal energy is emitted from one junction and is absorbed at the other junction, making one junction hotter and the other junction cooler. This phenomenon is useful in transferring heat from one medium to another at a small scale. The average energy of the electrons when they travel is different for different conductors due to multiple factors like the electron's energy spectrum, concentration, and scattering due to the amount of voltage applied. When current is made to flow, electrons move from one element to the other, and based on the direction of current flow, the electrons transfer their excess energy to the surrounding atoms. This energy transfer causes either the surrounding to emit energy or to absorb it. The Peltier heat generated at the junction per unit time Q is equal to pi A minus pi B whole into I, where Q is the Peltier heat, I is the current flowing from A to B, pi A is the Peltier coefficient of conductor A, and pi B is the Peltier coefficient of conductor B. The total heat that is generated at the junction is not determined by the Peltier effect alone, as it is influenced by both Joule heating and thermal gradient effects. In both Seebeck and Peltier effect applications, there are thermoelectric couples that consist of both positive and negative elements which are connected electrically in either series or parallel configuration. The third effect is known as the Thomson effect. The Thomson effect is a physical phenomenon where reversible heat is generated as electrical current is passed through a conducting material maintained at a temperature gradient. The Thomson effect describes the heating or cooling of a current-carrying conductor maintained at a temperature gradient. The Thomson effect causes the density of electrons at different points differing that are at two different temperatures, resulting in generation of potential difference between these 2 points. The heat exchange taking place in a current-carrying conductor maintained at a temperature gradient is given as Q equal to Kj del T and K equal to T ds by dt, where Q is the heat generated at the junction per unit time, K is the Thomson coefficient, J is the current density, S is the Seebeck coefficient, and del T is the temperature gradient. Let us consider two cases. In the first case, let us have a copper bar AB. Current is flowing from A to B. The bar is heated at the center point C. We see that the point C is at a higher potential. This higher potential at point C indicates that the heat is absorbed along the path AC and emitted along the path CB. Thus, the heat is transferred along the direction of the current flow. This effect is known as positive Thomson effect, as the heat transfer and the current flow directions are the same. This case happens for metals like silver, zinc, and cadmium. In the second case, let us replace the copper bar with iron bar AB, and the current is made to flow from A to B, and the center point C is heated. We see that the potential at the point C is lower, indicating that the heat is evolved along CA and absorbed along BC. Thus, the heat transferred due to the current flow is along the reverse direction of the current flow. This is known as negative Thomson effect. The previously discussed three effects, that is Seebeck, Peltier, and Thomson, these three effects combine to form the thermoelectric effect. The thermoelectric effect is a physical phenomenon where either conversion of temperature difference into electrical voltage or passing of electrical current into temperature difference takes place. In any thermoelectric equipment, a known temperature gradient generates a known potential difference of voltage. And similarly, a known voltage applied causes temperature difference between the two junctions of the electrical circuit. All the three thermoelectric phenomena, that is Seebeck, Peltier, and Thomson effects, are thermodynamically reversible. At the atomic level, the temperature gradient causes the electrons, that is the charge carriers, to diffuse from the hot side to the cold side. The thermoelectric devices are used as temperature controllers, as the polarity of the applied voltage determines the direction of heating and cooling. The interrelationship between the thermoelectric effects is as given below. K equal to del pi by dt minus S, where pi equal to Ts. K being the Thomson coefficient, pi being the Peltier coefficient, S being the Seebeck coefficient, and T being the absolute temperature. Thermoelectric effect is numerically expressed as J equal to sigma into minus del V minus S del T, where again J is the local current density, sigma is the local conductivity, and S is the Seebeck coefficient. The direction of flow of energy is considered to delineate Seebeck and Peltier effects. To describe the Peltier and Thomson effects, we must consider the flow of energy. If temperature and charge change with time, the full thermoelectric equation for the energy accumulated E dot is given by E dot equal to del into K del T plus del into V plus pi whole into J plus Q dot external, where E dot is the accumulated energy, J is the current density, pi is the Peltier coefficient, small k is the thermal conductivity, Q dot external is the external source of heat added, and capital V is the local voltage. Next we have the three laws of thermoelectricity. There are three laws of thermoelectricity, and they are law of homogeneous material, law of intermediate material, and law of successive or intermediate temperature. Here comes the law of homogeneous material. A homogeneous wire or a material is both physically and chemically same throughout its dimension. In a thermocouple circuit made up of homogeneous material, it is not possible to generate EMF even if it is maintained at different temperatures along its length and thickness. This law is extended as the law of homogeneous temperature, where thermocouples made up of different materials fail to generate EMF if the thermocouple is maintained at the same temperature. Thus, it is inferred that to produce EMF in a thermocouple circuit, the materials need to be different and maintained at different temperature at the junctions of the materials. It is also inferred that the thermocouple EMF is dependent on the difference of the junction temperature and independent of the temperature fluctuations along the length of the thermocouple wire. This is known as the law of homogeneous circuit. The second law is the law of intermediate material. This law states that introducing a third metal or conductor in the thermocouple circuit will not affect the voltage induced in the circuit if the conductor introduced is maintained at the same temperature. The algebraic sum of thermoelectric forces in circuit composed of any number of dissimilar materials is zero if all of the circuit is at the same temperature. The third law of thermoelectricity is the law of successive or intermediate temperature. This law of intermediate temperature states that the sum of the individual EMF developed in a thermocouple circuit with the junction temperatures being T1 and T2 and another thermocouple circuit with the junction temperatures being T2 and T3 is equal to the EMF developed by a thermocouple circuit with junction temperatures of T1 and T3 as shown in the figure below. The readers can refer to the following links and references for further and more detailed study. Thank you.